Uh, so okay, let's get started. uh, so 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 I posted the the lab assignment. Oh, where is the? So okay, okay. So uh, in this lab assignment, so you are requested to design the single cycle processor. So actually in chapter 4, so we are learning about the very simple single cycle so we learned the simple single cycle CPU design, and then this CPU just support several instructions. Okay, so and then but in this lab assignment, so you are requested to design the single cycle CPU, but this CPU needs to support more instructions. So as you can see, this CPU needs to support these instructions, right? Oh, where is okay. Also, you can find that. So this CPU needs to support the immediate instructions like add I, and then so additional logical instructions and SLT. So these are logical instructions and then end instruction. Also, this CPU needs to support additional branch instructions, right? So actually, in a textbook, the CPU supports the only BQ instruction, but in the the lab assignment, you need to design the CPU that supports more branch instructions. Okay, and then I believe you can uh, implement some additional instructions because in chapter, I don't know, in the previous lab assignment, so you designed the ALU that can support the additional instructions, like the exclusive or and then and the instructions. Also, for the immediate instructions, actually we don't need to modify ALU, right? So actually we can just modify the input of ALU, right? So in order to support the immediate instructions, the ALU just receive the immediate input, right? For the second ALU input, and then the ALU will generate the result, and then we can just store this result to the register file, and that's it. It's the same. But how about SLT? SLT is a little bit different, right? So what is the definition of SLT? Actually, we require, so SLT means that, what happened? Oops. Hmm? SLT. SLT means set ups, set less than. Okay. So it requires comparison between two register operands. Also, if we use the SLTI, then we need to perform a comparison between one register operand and one immediate data. And so anyway, we need to compare the two operands, and then based on the comparison result, then we need to store 1 or 0. The same means that set means, so I explained that. So same means we store 1, right? So it means if the compare, if we perform comparison, and then if the A is less than B, right, then we just store 1 to the destination register. So actually the other instructions, such as these instructions, and then these instructions just to store the result of ALU, right? So ALU just performs the the required operation, and then we can just store the result of ALU to the register file. But SLT is a little bit different because SLT just performs a comparison, and then we can use subtraction, right? So for comparison, we can just use subtraction in ALU, but SLT just stores different values, right? Like 1 or 0. So actually, we don't need to modify ALU for SLT, but for this single cycle processor design, but we need to add some elements in order to support SLT, right? Because so as I mentioned, though actually it's a little bit different. SLT just stores the different values. So, right. So, but in for this lab assignment, I provide the skeleton code, actually, right? So actually, I just provide the required variables for designing this single cycle processor design. Also, I provide some uh, hint or comments on the this on the system verilog file. Okay, so you can read my comment. Right? You can read my comment, and then based on the comments, you can design the single cycle process design. Okay, but then how can we design this SLT? So as I mentioned, okay, I will use some this slide. So as I mentioned, in order to support SLT, so we can use subtraction in ALU subtractor. Okay, so we can utilize the subtractor. But as you can see, as you know, the ALU so receive the two input, and then ALU generate the actually three outputs for our design, right? Because so our ALU has the 0 output, and then sign bit, and then result, right? So actually 0, we can use the 0 for BQ, right? But BQ or BNE, right? Because we can just check the result of AL, the result of comparison by checking the equality. So A minus B, we can just perform A minus B, and if this is 0, then it means the two values, two operands are so equivalent, right? If this is not 0, then it's not equivalent, right? And then for the sign bit, so we can actually we use sign bit for BGE or BLT, also SLT, like the BLT. So think about the BLT. So BLT means that branch less than, right? And then SLT means the set less than, right? So comparison is the same. So we just compare and two values, two operands, and then we just check the less than, right? But the next operation is just different. So you can use the sign output of ALU for SLT, right? Then how about the result? So how about the result? So other so arithmetic or logic instructions just to use result for in order to store the data to the register file. But how about the SLT? Actually, we need to define the different values in the single cycle CPU design, like SLT out or SLT result. I think the variable name is the SLT result. Okay. Then what is the value of this SLT result? It can be 1 or 0, right? So based on the comparison, so SLT result can be 1 or 0, right? And then, then how? We need to select the one of values, okay? If the SLT is executed, then we need to select the SLT result for the value which will be returned back to the register file. Or if this CPU execute other instructions, the other arithmetic or logical instructions, then the ALU result needs to be returned back to the register file. So I explained that if some condition, and then we need to select some value. If otherwise, so other condition, then the other result is selected. So I explained the behavior of a multiplexer, right? So I explained that some condition, if some condition, right? If a certain condition, then this value is selected. Otherwise, other value is selected. This is the behavior of a multiplexer. So what should we do? We can use the multiplexer for the output of, so we, in order to select the result from ALU or SLT result. Thus, you need to define this selection signal, and then this becomes the final ALU result. Okay, so in the previous lab, okay, so in the previous lab, so you were requested to design the ALU, right? But so you can find that so actually ALU, so this ALU can support the SLT also, but we do not add any special components or any special designs to this ALU, because we can just implement the CPU that supports SLT like this. Okay, we can just add multiplexer outside of ALU like this. Okay, so this is a little bit different. So even though we use the output of ALU, but we can just select some different result like SLT underbar result. So this is the special result for the SLT instruction. And then we can just select the one of result like ALU or SLT result based on the condition, right? And then you need to define this condition. And then this becomes the final output from final result from ALU, right? And then this will be returned back to the register file, right? Okay, so you can design the SLT like this, okay? So if you read the provided skeleton code, of the single cycle CPU, then you can also find some comments regarding this SLT. Okay. And then also I provide the test code. So this is the assembly code, and then also, this is the binary code, binary data. So, and then where is this data? So, this is the RISC-V assembly instructions. This is okay. This is the assembly code, and then this is the binary code, machine instruction, right? So where is this machine instruction? So in the instruction memory, right? So if you check the provided file, then you can find the imem dot mem. Okay, so which means this is the content of memory. Okay, So IMEM read this data. Okay, so and then this data needs to be equivalent to the data in this imem.mem file. Okay, so we initialize the instruction memory with these data, right? These are instructions, right? But it's the machine instructions, and then we just fetch instructions from the instruction memory, right? And then you can find that the number of lines of these two columns are equivalent. So what does that mean? This instruction is equivalent to this line. Okay. Also the next instruction. The next instruction is equivalent to the next line of machine instructions, right? So uh, during the instruction fetch step, so because this is the single cycle CPU, so I call it step, not stage. Okay, it's a step. During the instruction fetch step, then these instructions are read from the instruction memory. Okay, so which means you need to control the program counter of the single cycle CPU. So which means you also need to design the program counterpart for this lab, right? So we did not design the program counter in the previous lab, right? Because these are the components for the CPU design, not some basic data path element, right? But so for the instruction fetch step, so you need to design the program counter, right? So and then if you complete your single cycle processor design, then you can uh, verify your design using the test bench. So this is the test bench. This test bench system verilog file, and then I provide the complete version of the test bench. Okay, so if this test bench test bench is executed, then your CPU needs to fetch the machine instructions one by one from the instruction memory. Then your CPU needs to execute these instructions correctly, so appropriately, right? Then your CPU will update the what are updated by CPU, register file and memory, that data memory, right? So right, so so register file and data memory will be updated, right? So you can check the result. So you can check the result of your CPU, and then you need to verify. You need to verify your design, right? So if you execute the compiled code, so if you execute the equals Verilog, then your equals Verilog will generate this binary file, okay? And then you can just execute the binary file using VVP instruction. And then if you execute this file, then this file will generate where is the report.txt, okay? So if you read my test bench code, then you can find some statement that generate this report file, the report.txt. And report.txt will report the final states of register file and data memory, right? So we will check this report.txt to check your design is correct or not. Okay. And also the waveform file, that BCD file, will be generated. And then if you open this file, then you can find that this file is also the text file, right? So, and then by opening, by checking the, you can open this BCD file using GTK wave. So, and then you can check the waveform of your design. Then using this waveform, then you can verify your design. So, and then because I just provide this assembly code, then also you can just check the result of these instructions step by step, right? So this is the assembly code, and then we learn about the RISC-V assembly instructions in chapter 2, right? You can just check the output, the result of each instruction. Then you can also check the some result, the result of your design with the result of assembly code. Then if the the result is different, then you need to modify your design, right? And then also, so as you can see, these instructions include the load word, and then the arithmetic instructions, and then SLT, and PQ, PNE, also PGE, BLT. Okay, so actually, this assembly code includes most instructions. Most instructions supported by the single cycle CPU. So I believe you can verify your design using this code. Okay. Okay. Any questions? So, and then some student posted a question, but and then for this lab assignment, you don't need to uh, create the report PDF report. Okay, so you don't need to, right? You can just submit your design file, your system verilog files, and test bench. Okay, test bench file, and then report.txt. So this is the generated file, and then the waveform file, like the VCD file. So you need to just to submit these files. So you don't need to submit your PDF file. You don't need to generate your document, right? You don't need to. You don't need to, right? You can just submit these design files, and then the output of your designs. Okay. Any question? No question. And then also you can get you can get help from some TAs, right? So uh, if you have difficulty in designing these lab, so this CPU, then you can get help from TAs. Okay. Also, if you check the provided files, so actually you can find the completed data path element like instruction memory, register file, ALU, and data memory, right? So if you fail to design these database element in the previous lab assignment, then but you can use these provided database element, right? Also, you can compare your design with this provided database element, right? Okay, so okay, let's go back to the okay, so let's go back to the today's class. So in the previous class, we learned about the data forwarding, okay? And then, so I explained that in the pipeline architecture, in the five stage pipeline architecture, we need to support the three different types of data forwarding. right? So what are they? So firstly, the result is forwarded from the start point of memory. So this is the sampled ALU result, and then this result needs to be forwarded to the input of ALU for the next instruction. So this is the first forwarding method. And then the second forwarding method is the the ALU result or the result from the memory needs to be forwarded to the input of ALU. So all operands are forwarded to the input of ALU. It is because the following instructions use these data in ALU, right? These data in ALU. So the the sampled result by this memory write back pipeline register is forwarded to the input of ALU. So this is the second method of data forwarding. And then the third method is internal forwarding. Internal forwarding in register file. So internal forwarding means that when the data is being written back to the register file, this data can be also forwarded to the output port of register file, right? So this is the third data forwarding. And then we assume that the register file can support this internal forwarding, right? So in the pipeline design, so we do not consider this forwarding because this forwarding, the internal forwarding is supported by inside of register file. Okay. But so in the single cycle processor design, so actually, so our register file does not support this internal forwarding, right? Oh, no, no. No, right. So internal forwarding is not supported. Why? Because the forwarding is not required for the single cycle processor design, right? So within the one clock period, the data is written back to the register file and completed. So in the next cycle, the next instruction can read data, right? So actually the data forwarding is not required for the single cycle processor design, right? So this data forwarding is actually required for pipeline architecture. Okay, so that's why we are learning about the data forwarding in the pipeline architecture, right? And then our pipeline architecture needs to support these three methods of data forwarding, but this part, the internal forwarding is internally supported by register file. So actually, we will consider these two data forwarding method in the pipeline architecture. Okay, so 1 and 2. And then actually this internal forwarding. So in the last lab assignment, you will be requested to design the pipeline architecture. And then actually I will explain about this internal forwarding in the register file. Okay. Anyway, So in this class, we will learn about the data forwarding. So some architecture for data forwarding, but I will explain about this first and second method. Okay. So it is because these are supported by the pipeline architecture. But you need to remember that when the data is required, so when the forwarded data are required. And then I explained that the forwarded data are required by ALU, right? So I explained the data is forwarded to the input of ALUs, right? And then the data can be also forwarded from the start point. So it means the sampled output, the output sampled by pipelined register. So this data is forwarded. Okay. Okay. So firstly, we need to detect the forwarding condition. So what does it mean? So data forwarding is required for a certain condition, right? So data forwarding is not always required, right? But which condition? So obviously, like this. So in this example, so sub instruction generate the data, and then this data is stored in X2, and then following instructions are uh, require data from this sub instruction. And so the end instruction requires the forwarding method one. Okay, it's a forwarding one, and then the second instruction or instruction requires forwarding two, and then the add instruction requires the forwarding three, and then this is the internal forwarding, right? So then which condition? So, and I explained that we just consider this forwarding, right? But what condition? So the condition is simple. Register number. The destination register number of sub instruction, the former instruction, is equivalent to the source register number of the following instruction, right? So because this X2 is equivalent to the X2 of and then, this is the source instruction because the next instruction requires the data from the former instruction, right? So we can just check the register number between the destination of the former instruction and the source of the next instruction, following instructions, right? Obviously, right? So we can just check the register number. But, there are two source registers in the following instructions, right? In the RISC-V, the instructions can have up to two source registers, right? And then one destination register. So actually, in order to check the forwarding condition, we need to check the register number between the destination of sub and the source of and then another source. Source register number one and then source register number two. So these source register numbers need to be compared with the destination register number of the former instruction. Obviously, right? So this forwarding two is the same, the OR instruction. So in order to check the forwarding condition two, we need to compare the two source registers with the one destination register of the former instruction. Right. So if the register number is the same, equivalent, then we need to consider the data forwarding. Okay. Obviously, right? So, so this, so so we can just compare the RD and RS1 and RS2. So RD, the destination register number of the former instruction, and RS1 and RS2 of the following instruction, right? Then how? Then you can also check the you can find the pipeline register. And then what does that mean? So if you check this figure, okay, so you can find this narrow. So actually the ALU result in memory is forwarded to the input of ALU. Then, which means the forwarding is performed when the following instruction. So what is this? This is the end. End is here, and sub. The former instruction is in the memory stage. So because the end uses the data from the former instruction, sub instruction, when the end instruction is in the EX stage, right? Because end uses this forwarded data in the ALU, right? So end is in the ALU, and then the sub is in the memory stage. So in order to check the RD and RS1 and RS2 for the first forwarding condition, we need to check the RD in memory. So this is the RD of the former instruction. And then what is RS1, RS2? This is the RS1 and RS2 in EX stage. do you understand? Because, so you know, the sub is in the memory stage, and then this end, the end is in the EX stage. So and then I explained, right? So we need to compare the destination of sub and then the sources of end, right? So for the first forwarding, okay? So we need to check these registers. Okay, then what is RD in memory? So it means EX/memory. So this is the pipeline register. Okay, and then that register RD. So which means it's the output of pipeline register, but pipeline register is EX underbar mem, right? So this is the RD in memory, right? Because this is the EX/mem, and then so this is the RD. So and then this RD is in the memory stage. Do you understand? Hmm? And then we just compare the RS1 and RS2. So this is the first forwarding method. And then second, the second forwarding is performed when the sub is in the write back stage, right here, and then OR is in the EX stage, right? And then in the same way, so in order to detect the forwarding method number 2, then we need to compare the RD in write back and RS1, RS2 in EX, right? Because by the forwarding method number 2, OR instruction, so the instruction in EX stage uses the result in write back stage. So if we just compare this figure, then you can find that when the sub instruction is in the write back stage, this result is forwarded to the OR instruction, and then when the OR instruction is in the EX stage. Okay. So in order to check the second data forwarding condition, obviously, we need to compare the RD in write back. So which means it's the memory write back and then this result RD. Okay. So this is the RD sampled by memory slash write back pipeline register. And then we just compare this RD with the RS1, RS2 in EX stage. Right. So you can just understand some timing using this figure, right? And then this is the condition. So this is the baseline condition. So baseline condition means that, so we can just compare the RD of the former instruction and then RS1 and RS2 of the following instruction. And then based on the forwarding method, and then I explained about the three forwarding method, but in the pipelining, we just explain the first and then the second of the forwarding method, right? And then you need to understand when the forwarding is performed. Okay, so forwarding is performed. The first condition, the forwarding is performed when the former instruction is in the memory, and then the following instruction is in the EX stage. And then the second condition is the former instruction is in the write back stage, and then the following instruction is in the EX, EX stage, right? So based on this condition, we can just define the forwarding condition. Okay, so this is the baseline condition, but we need to also consider some uh, some boundary case. So which means even though these conditions are met, the forwarding sometimes the forwarding is not required when we need to check the reg write. Okay, so reg write becomes 1 if the register write is required. If not, then reg write is 0. But sometimes for some instructions, the reg write is 0, right? For example, store instruction, right? If the store instruction is executed, then this store instruction does not store data in the register file. Store instruction stores data in the memory, right? So the reg write is 0 for the store instruction. Also, another instruction is BQ or BNE, like branch instructions. Branch instructions do not store data in the register file. So for these instructions, so reg write is 0, right? If the reg write is 0, if the reg write of former instruction is 0, then the data forwarding is not required, right? So think about this. This is the store instruction, x1, immediate, x2, and then add instruction like x3, x1, x2. Then data forwarding is not required in this case, right? But you can think that, in the store instruction, there is no RD, right? So store instruction, just use RS1, RS2. Then why do we need to consider the reg write? So it is because actually we can just get RD from the instruction field, like so I don't remember the bit number, but like the instruction pin number, for example, 11 down to no 12 down to 8, right? So which means when the instruction is fetched, then the instruction has the 32-bit data, and then we just get RD from the some bit data from the instruction, right? Like instruction pin number 12 down to 8. For example, so I mentioned that I do not remember these pin numbers, right? What's the problem? Even though store is executed, then store does not have RD, but this field is uh, this field is occupied by other data, right? So this garbage data is given to the RD, even though the store instruction does not use RD. This is the garbage data, right? So if we do not include this condition, then if we based on this condition, then data boarding can be performed in the pipeline architecture. So we need to define exactly correct condition, right? So if we just define these conditions, then our hardware will operate incorrectly, okay? Because sometimes the data boarding is not required, but data boarding is performed by these conditions. So our CPU will generate the incorrect result. Okay, this is the critical bug, right? Critical bug. So we need to define exact and then the correct conditions. Okay, so this is the reg write, and then so we need to check the reg write. So which means if the reg write is 1, then we need to consider the boarding. If the reg write is 0, then boarding is not performed. Another condition is RD is 0. So why? So think about this one. Add x0, x1, add I. Okay. And then 1, and then sub x2, x0, and x3. So the sub instruction receives data from this add I, right, x0. And then what's the problem? x0 is actually always 0. So even though x1 plus 1 it has some values, but this value is always 0. What's the problem? If the x1 plus 1 is forwarded to this x0, then it will generate the incorrect result. Right? Do you understand? Because sometimes, so like the NOP operation, so we can just use the x0, like, so NOP means that no operation. So I explained in chapter 2, right? So in order to implement this NOP operation, we can utilize x0 as the destination register. But even though this is performed, but register is not updated, right? x0 is already 0. So in this case, but if this is forwarded, then incorrect values will be forwarded. So we need to avoid this case, right? So which means we need to check the RD number. And then if the RD the destination register number is 0, then boarding is not performed. Okay. We need to also check this condition, right? Okay. So as I mentioned, actually in the hardware, when the hardware design, we need to check all conditions, right? Because so even though you can think that oh, this is very special case, but the hardware needs to consider all cases, all possible cases. Otherwise, the hardware will generate the incorrect result. It's bug, and then it's just then the hardware will not operate correctly, and then this hardware is called a stone, right? Tool. Why? Because we make a CPU chip using a silicon SiO2. Silicon is Si, so silicon is Si, and then usually SiO2 is the element of rock or stone, right? Or sand, right? So if the CPU does not work correctly, so it's just stone, right? It's because it is composed of silicon. Actually, the component is the same to the rock or sand. Okay, it's called stone. Actually, anyway, so then how can we implement the boarding path? So when I explain about the data boarding, when the data boarding is performed, then ALU receive boarded data. If data boarding condition is detected, otherwise ALU receives no more data. So why did I explain this? Some condition, it received boarded data. Otherwise, it receives normal data. It can be multiplied, it can be implemented by multiplexer, right? So I explained for some condition, if some conditions, then it receives some data. Otherwise, it receives normal data, other data. And then we can implement this behavior using multiplexers, which means we can implement the boarding path using multiplexers, right? So, and then the data is forwarded to the input of ALU, so we can locate the boarding multiplexer in front of the input of ALU. So you can find the multiplexer here and then multiplexer here. And then these multiplexers receive normal data. So this is the normal data from register file, the operand from register file, and then boarded data. But I explained that there are two boarding methods, right? So there are two boarding paths, right? So this boarding multiplexer receives three inputs, and then it's selected by some control signal, the selection port. So this is the selection signal. It's called the board A, and then it has the 2-bit signal because there are three inputs. Also, the ALU has the two inputs. So actually, so the data can be forwarded to the second input of ALU. So we need to have two boarding multiplexers, and then it's controlled by board B. And then also you can find the boarding unit here. and then if this forwarding multiplexer is working in the EX stage, so forwarding unit is also in the EX stage. So we just use the control signal generated for the EX stage. Okay, then you can find that RS1, RS2 is given to the this forwarding unit. And then what is this RS1 and RS2? So as I explained, this RS1, RS2 is the RS1 and RS2 in EX stage. So this is the output of EX, no, ID slash EX pipeline register. And then we also learned that this RS1 and RS2 is compared with the RD in memory, right? So this is the RD in memory. So this is called for the forwarding method number 1. Okay. And then also you can find that the RD is forwarded from the memory stage. So this is the RD in, no, write back stage. So this is the RD in write back. Okay. So forwarding unit received the this data. Also, as I mentioned, the forwarding unit needs to receive regular signal. So, right? And then also we need to check the RD. So if the RD is 0, then forwarding is disabled. Okay. So forwarding unit receives these signals in the EX stage, and then it generates the forward A and forward B. So it's a selection signal for the multiplexer. Okay. And then as you can see, these multiplexer receive. So you can find the data from here. Okay. So where is the okay? This data is connected to the second port, and then this data is connected to this port. Okay. And then you need to check that actually when the data is forwarded from the write back stage, then this data, this result is forwarded. And why? The data can be also forwarded from the memory instruction, like load instruction. So this is the final result. So actually we need to forward the output of this multiplexer. And then this multiplexer receives the data from data memory and then the data from ALU, right? So this final result, the final result needs to be forwarded from the write back stage, right? Okay. So this is the forwarding path in the pipelined architecture. Okay. So data forwarding can be implemented like this. And then this is some control. So if the forwarding A is 00, then source is the ID underbar EX. What does that mean? This is the normal case. Okay. The forward A is 10, then the data is forwarded from the EX slash memory. So this is the data in memory. So this is the forwarding method number 1, right? And then if the select port A selection signal is 01, then this is the memory slash write back. So this is the data in write back is forwarded. So this is the forwarding method number 2, right? So we can just define the forwarding condition like this, and this is the same. The build B is the same, right? So we can just summarize the forwarding condition like this. Okay. So But another corner cases. Another corner case is this one. So what's the problem? So problem is for this add, the source register, this one can be forwarded from the second add number two, and also this x1 can be forwarded from the first add, the add number one, right? So which means, so based on this condition, okay, so forwarding number one is true. So the forwarding number two is true. Then which data needs to be forwarded in this case? Number one or number two? So this add or this add? Obviously, this add. The data from this add needs to be forwarded. Why? Because this add generates the latest result, right? This is the final result of x1, right? Do you understand? So both conditions are true. So in this case, we need to decide which data needs to be forwarded. But in this case, we need to select the latest value, right? Obviously, because the instructions are executed from top to bottom sequentially. So this is the latest value. Then we need to forward the latest value to the next instruction, right? So if the both conditions are true, then we need to select the forward method number one, right? Not from this one. The I explained is this is the forward method number one. So which means the result in memory needs to be forwarded. And then this forwarding has higher priority than the forwarding method number two. Do you understand? Do you understand? So both forwarding, so result in write back and then result in memory can be both forwarded. In this case, we need to select the result in memory because this result is the latest result. Okay. So actually the forwarding condition becomes more complex, right? So this is the revised forwarding condition, right? Uh, but you can just remember that actually the forwarding condition has priority, and then actually we can have we can give the higher priority to the forwarding method number one compared to the forwarding method number two. And then in the hardware design, this priority can be easily implemented using if else statement, right? So you know the if else actually has the priority. If condition one has the so like the if A and then else if B. If we write the program code like this, then actually this condition A has the higher priority than condition B, right? Right, right? Because if the condition A is true, then it's just true. And then this is ignored. Condition B is ignored, right? So if we use the if else statement, So in the system Verilog, you can also you also use the if else statement, right? So actually we can easily implement this priority control, the higher priority for the condition A actually. Okay. Okay. So this is the complete forwarding path in the date for the data forwarding, right? So as you can see, you can find the forwarding mux multiplexers here, and then forwarding unit. Forwarding unit detects the forwarding condition, and then also we need to check the control signals, okay? Because we need to check the regulate signal, okay? So we also the control signals are given to this forwarding unit, okay? So by doing this, we can implement the data forwarding in the pipeline architecture, okay? So you can think that, oh, pipelining is easy to understand, but actually, for the implementing the data forwarding it's a little bit tricky, right? But it's okay. It's actually because this is the corner case, okay? So actually, even though the basic concept is easy to understand, but we need to also consider the corner cases, and then actually this part is more difficult. It's a tricky part in the pipeline architecture. Okay. Okay, but also, okay, this is the data forwarding unit, and then we have just 5 minutes, and I will briefly explain about the pipeline stores by hazard. So for the data hazard case, we learned that we can handle data hazard using data forwarding. But if the formal instruction is load instruction, okay, where is the load instruction? So like this, okay. If the formal instruction is a load instruction, then we cannot handle this load use data hazard using data forwarding. So which means the one cycle will be wasted. Then how can we implement this behavior in the pipeline architecture? So actually, conceptually, we just learned that if the formal instruction is load instruction, and then the destination is the same to the source of the following instruction, then one clock is just wasted. That's what we learned conceptually. But we need to implement this concept in hardware architecture. Then how? We can implement this behavior using pipeline store. So pipeline store means that, so pipelining means that if one task is given to the first stage, then this task is transferred to the next stage, right? Next stages and every clock. This is the pipelining. Pipeline store means that this pipeline, the data transfer is stopped. Okay, so it is called the pipeline store. So which means if this condition, for example, if the formal instruction is the load instruction, and then the destination of load instruction is same to the source register number of the following instruction, the very next instruction, then the execution of this next instruction is stored in the pipelining. So it means it stops in a certain pipeline stage for one clock, right? So this is called the pipeline store. So which means in order to support this behavior, we need to implement the pipeline store. Okay, so the propagation is stopped. So in the next class, we will learn about how to implement this pipeline store by load instruction. And then we will learn about the control hazard, because and then I believe we can just cover some of these pipeline store cases. Okay, thank you for your attention, and see you in the next class. 감사합니다.